dipole antenna is one of the commonest antennas used by amateur radio operators. Actually, it is a half-wave dipole antenna, meaning that the whole length of the antenna will be half of the wavelength of the operating frequency. That means a 40-meter antenna will have a total length of 20 meters and a 20-meter antenna will have a total length of 10 meters. Each side of the antenna will be 1/4 lambda on both sides. So 10 meter of wire to either sides will constitute a half-wave dipole antenna for the popular 40-meter band. Ideally, you have to take into consideration the velocity factor of the material with which the wires are made, that is copper or whatever you are using. Earlier, in the beginning of my ham radio career, I used to use uninsulated copper wire. But now, myself as well as others are using insulated copper wire for the elements. Initially, in my early days, I never knew about the balun. This is the balun. That is, this is a current balun I am using here. That is because dipole antenna is a balanced system, while the coaxial feeder is an unbalanced system. So feeding a balanced antenna to an unbalanced feed line, you need what is known as a balun at the feed point. Usually used is 1:1 current balun. Reason why this is needed is that in a coax there are 3 currents. One through the central conductor, another through the inner aspect of the coax, and another through the outer aspect of the coax. There are 2 currents flowing through the shield. That is, on the inner aspect you have one current, outer aspect of the shield another current. The current in the central conductor and the inner aspect of the shield are opposite to each other in phase, 180 degrees. So that is okay. But this is an additional current, and this additional current is known as common mode current. This common mode current can cause the antenna system to radiate along the feed line, not only along the antenna elements but also along the feed line. It can radiate. To suppress this common mode current, this 1:1 current balun is used. And typical impedance of a half-wave dipole antenna is around 70 ohms. That will match fairly well with the usual 50 ohms impedance of the radio. And minor differences, most of the modern SDRs, software defined radios, have an auto tuner like my FT710 radio that can touch up any mild difference in the impedance between the radio feed line and the antenna. Usually most of the amateurs mount half-wave dipole antenna as an inverted V like this, with an angle about 90 to 120 degrees. That is what I have also done, and an inverted V half-wave dipole antenna. And the dipole antenna has a radiation pattern like a dumbbell. There will be waves going in this direction and in this direction. That is not single plane, it's actually a 3-dimensional dumbbell shaped radiation pattern along the long axis of the antenna. Radiation along the ends is very minimal. Both ends radiation is very minimal or less. So dipole antenna has also a selectivity or some sort of directivity in two directions. It can be considered as a bidirectional antenna, and it has some gain compared to the isotropic antenna. Isotropic antenna is a spherical theoretical antenna in which radiation is all around in a sphere, not in a circle, a sphere all around. That is the isotropic antenna. And a dipole antenna has a gain of 2.15 decibels in comparison with a theoretical isotropic antenna. When we actually make a dipole antenna, you have to think of the supports. For a horizontal dipole antenna, you need two elevated supports on the sides. That is what we have shown here. But if you do not have provision for two tall supports on the side, then inverted V antenna comes in handy. For inverted V antenna, two supports on either side need be only very short, while a single central support has to be tall. And these side supports have to be in locations where they are not accessible easily to animals and human beings, because when the dipole antenna is active, the voltage maximum is in this region. So there can be significant radio frequency voltage if you touch that region. That is why we now use only insulated copper wire, and the tip also we will insulate. So we do not want RF burns. Radio frequency on contact will produce superficial skin burns which are difficult to heal. Not like usual electric shocks, radio frequency usually causes burns. So we do not want to have that to happen. And the risk increases as the power output of the radio increases. That is a caution with a inverted V dipole. Then usually we have this support, central support, it is, and both supports on the sides. Better that they are of non-conducting material. But there are many of us who use GI, galvanized iron pipes as well, and fairly get along with it. But recommended is non-conducting posts or mass. Then there should be insulators at both ends so that the RF does not flow into the mast, especially when it is wet during rain. And the height of the side supports in case of horizontal dipole antenna, ideally it should be at least quarter wavelength. That means at least 10 meter for a 40 meter antenna. Most often we may not be able to get that. We will have mounting in such a way that it the best possible in our situation. Another aspect to be thought of regarding the height is that in case of antennas, height is might. That means the higher your antenna is placed, better the propagation. Another disadvantage of low mounted antenna is that they are sometimes called as cloud burners, because most of the signals go vertically up rather than at a low angle. If signals go at a low angle, they can get reflected from the ionosphere at a longer distance. If they go straight up, they get reflected at a shorter distance. That is known as Near Vertical Incidence Skywave propagation. That is useful for short range propagation, especially in hilly areas where you want the hill to be covered. In hilly areas, the horizontal or low angle radiation will not be successful because that will be blocked by the mountains. So NVIS is the usual mode of propagation if the antenna height is less. NVIS can also be enhanced by keeping a reflector here. Suppose you have a same length wire kept below that, then there is a chance of increasing the NVIS propagation in dipole antennas. While mounting dipole antennas, it will be useful to have pulleys at both ends for a horizontal dipole antenna. If you have pulleys here on both ends, there are two uses. One, if we want to lower the antenna for tuning purpose, or suppose you want to repair something, change the balun or anything, it is easy to bring down the antenna. You don't have to bring down the supports. That is one reason why you use pulleys at both ends. Another reason is that horizontal dipole antenna, the center part will sag due to the weight of antenna elements as well as balun. Balun is much more heavier because it contains a ferrite toroid. So, and the balun box, insulated box. So this portion will sag. To prevent that sagging, there can be a weight attached here. On both sides, if a weight is attached, then the central sagging of the antenna can be reduced. In case of inverted V antenna, that is not so important. Even then, pulleys on the lower supports will be useful in keeping the antenna wire taut. And in that case, pulley at the central region also is there. That is for lowering the antenna when needed. You may be aware that when you make a dipole antenna, it may not always have a good 1:1 standing wave ratio. Our aim is to have a good standing wave ratio. For that, earlier I used to use SWR meters to check the SWR on different frequencies of the band, and then depending on the direction in which the SWR is increasing or decreasing, I used to either trim or lengthen the antenna elements. Suppose the lower end of the SWR, then later I moved on to nano VNA. In nano VNA, it is much more convenient because nano VNA sends out 101 frequencies in a selected range. Suppose it's a 40-meter antenna, I might select between 6.5 to 7.5 megahertz as the test range in nano VNA. Then what happens is that it will show a graph that is something like this, and this point will be the point of minimum SWR. Suppose this point of minimum SWR is below the 40-meter band, say at 6.8 megahertz, then it means your antenna element is longer than what is required. You have to trim it. Instead of trimming, most often we just fold back the elements and twist them so that it is almost equivalent to trimming, not exactly equivalent. Why we do folding back is because trimming is an irreversible process. If SWR doesn't come into the range which you require, then you will have to join a piece. But if you fold back, it's easy to untwist and fold back to increase the length as well. But if this is the other way around, suppose it is resonating at 4.5, then to bring it to the 7 to 7.2, that is the band range here, then you will have to lengthen. And while lengthening, there is one more method. You suppose the space in your region is less. Instead of lengthening it like this, because the supports will be fixed availability, you can add a piece here hanging down. Both ends you can add equal length of pieces hanging down. That will also give the effect of lengthening. That is, these are two tricks for tuning: folding back for reducing length, for increasing length attaching a piece and having it hanging down instead of getting the supports in different directions. Sometimes you may have a longer distance here available at home and you would have used a nylon rope or something in between, then it's easy. Otherwise, when the space is constrained, you can increase length by dropping down a piece. This can also be used for lower bands when your mounting space is not enough for mounting that particular band antenna.